Okay, welcome everybody. Today is our continuation from where we left last time. So basically, we mentioned that we use dendrimer dipole excitation technique for T-ray generation, and this way we can generate wide band with T-ray, and also power is tunable. So the dendrimer itself, by itself, is not a high Chi2 material or doesn't have higher electro-optic coefficient, which is needed for conversion efficiency, higher conversion efficiency from pump laser to T-ray. So we dope it with the chromophore. There are many chromophores that can be used. Actually, we chose one. We chose one based on the molecular size. We chose a small molecule chromophore. It's called alizarin. I don't know if it means anything, but it has a chemical formula. But there are many of them in the same family that could be chosen. So the key thing here to see the absorption characteristic and emission spectrum. Those are two things that matters. So, like I said last time, by itself, when you dope, you have the dipole generator, dipole population generated in the molecule, within the molecule, around the molecule, etc. But those dipoles are, by itself, they have a random distribution. So if you see upper left corner, figure A, that's kind of a sketch of how the dipoles are generated. Then there is a process called polling in figure B on top line. And what it does is it aligns the dipoles, and that alignment is very important. Higher the alignment, higher the electro-optic coefficient. It's called uniaxial polar material. And then we measured the refractive index by a machine called prism coupler. This is an instrument produced by a company called Metrology in New Jersey. So they were kind enough to evaluate our samples. We produced the, we supplied them with the poled and unpoled dendrimer sample. They measured the refractive index as a function of wavelength. As you can see on the upper right corner, because of polling, the refractive index has changed. So we can now calculate the delta N, and the purpose of that delta N is to be able to calculate the refractive, the R33 parameter, which is related to Chi2. So here, as you can see, let me get the pointer. So this here is showing that as here's the experimental setup, number B. We have that dendrimer sample, apply the, voltage can be varied. So we have a 20 kilovolt supply, and the minimum threshold is about 6,200 volt. But as you increase the voltage, the corona current is corona pulling system. So corona current keeps going up, but after certain, at certain point, it saturates. That indicates that all the dipoles are now aligned. At that point, so initially the sample is, before polling, is taken at a little bit higher temperature, approximately near its glass transition temperature. where materials are, the dipoles are not rigid, so material is a little bit fluid, therefore dipoles can align. When all the alignments are done, then temperature is turned off while the voltage is maintained. So then all the dipoles get frozen in their place. And that's how the, the electro-optic coefficient goes up, which is related to the second order susceptibility. And the measured value for R33, although there is a dispersion as a function of temperature, as a function of wavelength, but still it's pretty high value compared to other materials like lithium niobate has 32 picometer per volt, gallium phosphate has 1.1 picometer per volt. Dendrimer has 130 picometer per volt. It can also be further tweaked. But the point is, lithium niobate, although it has a relatively higher electro-optic coefficient within the inorganic family, but still lithium niobate is not good for producing T-ray. But gallium phosphate is, but that's in microwatts or so. So,
a quick question, Dr. Rahman.
Yes, please.
For the bottom left, plot, what was the temperature here?
It's about the glass transition point of this dendrimer, which is I think about 120 or so degrees Celsius. I'm not absolutely, I don't, it's all in the notebook and in the literature as well. We have.
But it has to be above. Does it have to be above the glass transition temperature?
No,
or
it has to be near, because
Okay.
above the glass transition points, material will change.
Oh.
So we do not want it to change. We still want the dendrimer, except that the charges should be fluid enough so that it can get aligned because of the field.
But if it did get, like, for example, 120 degrees C is your glass transition temperature here. If it goes below 100 degrees C, does it significantly change this response?
If it is below 120, I mean, let's say the glass transition point. If it is significantly below, then dipole alignment will not be very efficient. So the whole point is that we want a unipolar material, high electro-optic coefficient. And, we had to do some tweaking. Quite a bit of experiments went into this, getting it right, because the concentration of the chromophores is also important. So if we have too little chromophore, then not enough dipoles, and if we have too much, then also it has stability issue. So the doping has to be just right as well. And we can do some calculation, but experimental determination is very important. So all of those things had to go into the consideration. It took us more than a year to get this thing done right. But yeah, quite a bit of experiments was done actually.
Say you are fixed with 110 degrees C to get this. So you have to maintain this 110 degrees C for your T-ray generation all the time?
No, not for T-ray generation. For cooling process, the temperature need to be maintained.
Okay.
But after the polling is done, then like I said, it's all it matters is absorption characteristic and emission characteristic, and that is at room temperature, not at elevated temperature.
Oh, okay. That's good to know. Thank you.
Yeah, right. Any other question?
No, this is good for now.
Okay,
thanks.
Wonderful. So let's move on. You have seen this in the past. Here's the absorption happening, and there is the emission happening. So the emission is broadband, but this is a new graph. As you can see, the source power is very stable. And this is very important, both for imaging as well as for spectroscopy. It's more important for spectroscopy than imaging. So when we come to spectroscopy, as you will see, I mean, we have long-term stability of this source. Even inorganic don't have this kind of stability. Their power fluctuate. But it's important that we get very, very stable power. It's about 220 milliwatts of power at CW. It's a big deal, so to speak. So
what's the reason in the very beginning? You can hear me, right?
yeah.
In the very beginning, I see a spike close to the 0 minute. Do you know why?
Yeah, it is the pump laser takes time to stabilize. It is not the T-ray source.
Okay.
Because it's a process where a pump laser is used to excite the dendrimer dipole. Therefore, the pump laser power has to stabilize, and it takes maybe 3-4 hours. I mean, our specification is half an hour, but often in half an hour, it stabilizes, but still is not good enough. So we always allow time to let it stabilize before the measurement. Good point.
And you are using, if I remember correctly, femtosecond pump.
No. It's a CW. So
It's a CW, okay.
biggest, we have quite a few, how should I say, deviation from traditional terahertz generation. One of them is we don't use femtosecond pulse laser, because that femtosecond pulse laser by itself is an emerging technology. It doesn't actually, so, come to think of it, let me show you this one.
So both the pump and the T-ray are CW.
No, yeah, pump is, yeah, both are CW, exactly.
Okay.
Exactly. So this is a femtosecond pulsed laser. Actually, we started this way because that was the knowledge base available when we started doing this. So this is the top one is the laser itself, laser head, and this is the controls unit and the water pump. So this is, as you can see, it's a huge deal. And this thing we borrowed from a company in Austria, which cost about 150 to 200,000 euro. So it's very expensive. And one we got was about, it produced probably about 50 or so femtosecond pulse packets. So also the femtosecond pulse laser is kind of a misnomer because they have packets of, kilosecond time period packets, laser packets. Within that packet, they have femtosecond distribution. So the sample doesn't see the femtosecond pulse. It sees kilosecond packets of femtosecond pulses. So I think we are very fortunate that we have been able to eliminate this thing. And then we're dendrimer dipole excitation, although as I said, in the review paper, is kind of not very widely known and used. So that's a good thing and bad thing, because good thing is all our patents are very clean, and bad thing is that it's not very widely known yet. And so today, what we're gonna do with this review, we are gonna get into some of the problems, some of the actual applications. So why semiconductor is so important, and how the imaging helps. Those are the things we would like to get into today. But if you look at on the outset, these are the wafers, this single wafer. As I showed last time, the bowl is sliced into wafer and polished, then it becomes wafer. Of course, it needs to be doped, either N-type or P-type. Now, each of these blank discs may cost $100 to $200, not more than that. But on one of those blank discs, when all the die are made, this day, the die size is 2 to 3 millimeter by 2 millimeter. 2 millimeter by 2 millimeter die size, and then space is left for slicing. So if you do the calculation on a single wafer, 300 millimeter single wafer, there will be more than 10,000 chips or 10,000 die on the wafer. Then they are, sliced, singularized, then electrodes are attached, packaged, and then used. So if you think about the economics here, this $200 wafer, when you have all 10,000 die on them, its value increases significantly. And if one chip is sold for $100, there are cheaper ones. Not all of them are high value. But even for per chip is $100, that 10,000 times $100 becomes $1 million asset. So defect detection is important, because to build these chips, there are many layers are patterned one on top of another. So if they have a hidden defect in one of those layers, which is not on the surface, then there's no obvious way of understanding what the defect is and getting a remedy of that. So T-ray, because it can see below the surface, has tremendous advantage in metrology applications. So in summary, then semiconductor manufacturers need less than 1 nanometer resolution, because if the line width is now 2 to 3 nanometer, and in that 3 nanometer, if there is some defect, then one needs to have very high resolution to be able to see them. So the current art is optical X-ray, atomic force microscope, scanning electron microscope, transmission electron microscope, etc. None of them can see what's below the surface. And they see only one, if you get an image, only one image at a time, one surface at a time, frozen in time. So there is a need for new capabilities. So in part one, then we'll go into imaging. Imaging is the basis for metrology. Imaging is not for imaging. Of course, seeing is believing, so we see, but we also measure from the image. And that is the whole point of having a imaging system with very high resolution. So first we'll talk about the cameraless T-ray imaging. Cameraless, understand there is no camera or CCD or that kind of device that is gonna create the image. And the reason is that when you want to decouple the wavelength, remember with all the imaging system out there, RB diffraction limit limits how small object we can see, and we'll discuss that. So we need to get lattice resolution, but we need to get with bigger wavelength. T-ray is big wavelength, not electron wavelength, not X-ray, etc. And then we need to do the volume imaging and layer by layer, and then the metrology. So nanometrology, and again, the metrology is a term that we will be using throughout a lot. So, metrology is basically the science of measurement. All different kind of measurement falls under metrology. Here, of course, we are going to be focusing only on semiconductors. And as the jargon goes, if you cannot measure it, you cannot control it. So if anything that we do in science and technology, measurement is the key. And then the challenge is, of course, using bigger wavelength and get high resolution image without electron microscopes and AFMs, etc. So what is Abi diffraction limit? It is in 1873, German scientist Ernst Abi. He established that when you are using microscope, the smallest object one can see cannot be smaller than half the wavelength of the light that is being used for imaging. So for UV, that is on the shorter wavelength side, 256 or so nanometer wavelength. So with UV, then we should be able to see half of 256, 128 nanometer. But atomic lattice is way smaller than that. And that's why the electron microscope comes, because the electron wavelength is in picometers. So, 10th of nanometer is the atomic lattice. Electron microscope can see that. In real electron microscope system, the resolution is still about 10 nanometers, 10 angstrom or so. So they still have to do some technique. I have used the electron microscopes for my dissertation work. It's not an easy task. Even today, although with all the improvements, using an electron microscope, learning it takes a while. One need to spend a lot of time, which I did. I think as far as I remember, late 80s, we had that electron microscope images where we saw nanomaterial. A paper was published around 2000 or so. And I believe that we are the first group reporting the nanoparticles from TEM image. That was a tin oxide system. If anyone interested, I'll be happy to share that with you.
What is the scanning time between these instruments, and maybe the prep time?
Scanning time for the terahertz. Okay, I'll come to that.
Okay.
Yeah, let's So challenge here is to overcome the diffraction limit with bigger wavelength. So the diffraction limit says that you cannot see less than half the wavelength. So what we're saying is that is overcoming the diffraction limit enough? And we are making the point here that it's not. Because T-ray, particularly T-ray, its wavelength starts around 9 micron and it goes all the way to 3 millimeter. So even on the shortest 9 micron, if we can have an image less than 4.5 micron with T-ray, that breaks the diffraction limit, that overcomes the diffraction limit. But does that give us lattice resolution? No. We are far away from achieving the lattice resolution. So the question is, how do we do that? So we have decoupled, it's a wavelength decoupled imaging technique that we have invented. And we use the Beer-Lambert's law, or modified Beer-Lambert's law, in terms of the reflectance. And then we digitize a volume by our nanoscanner. And then we use algorithm for image generation. So this is our instrument. I probably have shown you last time, but this is a free space system, meaning that the sample is held somewhere here. This box can go up and down with this vertical stage. And then it can focus in vertical incidence onto the sample. And then the scanner moves around the sample to get the, the intensity matrix, Beer-Lambert reflection matrix, and then the computer generates the image. As opposed to that one, this one is a fiber coupled beam delivery, because if your wafer is very big, 300 millimeter and above, any sample, not only wafer, it can be any sample, then putting it on a scanner and moving the sample around causes vibration, even when the vibration is isolated by, pneumatic system. So we don't want to take any chance. For bigger sample, then beam is delivered by a fiber. And this is a module that is added to this scanner so that the beam itself can scan the sample. So that's the only difference. Other than that, everything else are identical. So these are the two configurations, and in each configuration, then you can have only imaging, and you can also have imaging plus spectroscopy. So
one question, excuse me.
Yeah.
One question.
Sure.
So now you have the stage, excuse me. The wafer is fixed, the position wafer is fixed, right? Wafer is not moving, number one.
On this one, wafer is moving, on the left one. On this
the right one,
wafer is not moving.
Okay. Now you have the stage for doing the scanning part, X, Y, and Z, all three directions, right?
Yeah.
Okay.
Exactly right. Yeah.
Okay.
And in each direction, we have very high resolution, nanometer resolution of the stage itself. I think it's appropriate to point out that sometimes there is a theta axis as well.
Okay.
So the theta axis is needed under some conditions, because here the beam is getting vertically onto the sample, which is also vertical. But in another configuration, when I have bigger sample, we may want to put it on a gantry system, and then sample stays flat, and the theta axis then can be used to direct the beam vertically onto the sample. So that those options are also there. I'm not showing here for simplicity purposes. So already complex enough. So.
Sure.
So these are the instrument that our company make.
But on the right side of this stage, you have X, Y, Z. Do you also have theta movement here?
No, this one, I don't think there is theta here. There are other systems where the theta, if I had theta, then this module would have been connected to the rotary axis, as opposed to being connected to the Z-axis. That's the only difference.
I'm sure you're going to talk about the matrix, lattice, etc. later. And for that generation of the data, are you using all three axes, X, Y, and Z for this?
Absolutely.
Okay.
Sure. All three axes are being used. Yes. Any other question at this point?
That's good. Thanks.
Okay. So these are some of the, installations we have, some laboratories, and just to show this. So one question comes that when we are scanning an object, where does the contrast come from? The image is the distribution of intensity. So the intensity distribution comes from the fact that every material has its characteristic reflectance. For example, if you have a metal line on a semiconductor, right? So when the beam hits the semiconductor, then we'll have a reflectance. And if beam moves onto the metal, then the reflectance will change. So a wafer, on a wafer, a chip is periodic arrangement of materials, if you can think it that way, in all three directions, right? In XY direction, the material distribution, also along the Z direction, there is material distribution. So if on a surface, for example, here, what I'm showing is if you scan on a surface, based on the materials, we get different intensity, reflected intensity. That's the basis for making the image. And the other thing I'm showing here on the left, reproducibility. If I scan this same object over and over again, then I should get the same reflectance. So these two are important. The source stability determines how reproducible these scanned traces are. As you have seen before, we have a very stable source, therefore we get highly reproducible scan. And couple that with the fact that the reflectance is characteristic. Therefore, we can explain the reflected intensity in terms of a modified Beer-Lambert's law. And Beer-Lambert's law, of course, originally used for chemical concentration. So instead of concentration, which is, in this case, instead of C, it would have been C, we have used a material parameter. For example, dielectric constant, but it could be refractive index, it could be even density. Some material parameter can be used here instead of the concentration. So, the molar absorptivity and the path length, they can be fixed, but molar absorptivity, of course, fixed for a given material, but path length is the geometry, experimental geometry. So if the refractive index or dielectric constant, in this case dielectric constant, is not changing when the sample is mounted on the stage, that's not changing. So whatever path length is changing is giving us the concentration, the intensity gradient, intensity variation. But of course, dielectric constant changing when the material changing. Therefore, that's also contributing to the intensity variation. So that intensity variation also can be modeled in terms of either dielectric constant or something else. So that's a different issue. But for image generation, this intensity matrix is the more important.
A question.
Yes.
If you can go back, yeah. So, for example, you're scanning in an XY plane. Now, the only parameter is changing here with the scan, as you scan, only one parameter, is that right?
Intensity, yeah.
Out of these three parameters, alpha, L, and epsilon, the absorbability is fixed constant. Dielectric constant is constant. Only the path length is changing here in the XY plane.
Actually, absorptivity, the dielectric constant is fixed for a given material.
Okay.
But the chip is a distribution of materials. So that's changing from material to material. And that's contributing to the reflected intensity.
So for a given spot, fixed spot, XY on the XY plane, you still can detect the depth and different materials on the same spot.
Sure.
Okay.
Absolutely. As I will say later, that the spot size is not important for image generation, unlike microscope. Everywhere else, spot size is important, but when we decouple the wavelength, spot size is not important because it's not wavelength dependent imaging. It's wavelength decoupled imaging. So we'll come to that. Main comparison between a camera system and camera-less system is shown here. On the top, what is in a camera? We have an object that is focused via a lens system onto a charge couple device inside the camera, or it can be a focal plane array, some kind of focal plane array. There's CMOS technology and so on and so forth. Bottom line is the pixels are made on this little chip. It's called focal plane array. So this image of this object is going and falling onto that focal plane array. That device produces proportional voltage based on this, contrast from the object. And those signal, there is an ASIC inside the camera, ASIC inside the camera, or application specific IC, kind of a computer chip, right? That generates the image. So that does the image generation, manipulation, storing, etc., etc. So what we have done here is we have replaced the CCD and the focusing system by this nanoscanner. There is a focusing system here. Focal point can be moved around, but instead of CCD, we have this nanoscanner. So the nanoscanner produces the reflected intensity matrix, what we call is the Beer-Lambert reflection matrix, because it follows the Beer-Lambert's law. And it's important to recognize that it's a law, Beer-Lambert's law. It's not a hypothesis, not a theory. It's applicable wide variety of things because of this nature. So it holds. Wherever the reflected matrix is generated, the law holds. And then what we do is once the matrix is generated, then we use a computer algorithm that generates and manipulates the image. So why is all this trouble? Are we not happy with a CCD-based camera? I mean, yes, of course, if you want to go for a photo shooting or nature, etc., be good. But for scientific imaging, a CCD has, if it is 100 megapixel, it is 100 megapixel. We cannot change that. So if we want to change, if we want to make our own pixel size, that's what is done by this nanoscanner. Because user now can choose how fast and how slow to scan. Faster scan produce bigger pixels, slower scan produce smaller pixels. And on top of that, when we scan in 3 dimension in a volume, we call it a voxel. So camera is never able to produce a voxel in 3D. So that's important. When we say 3D, it's not just the surface image, as in electron microscope or AFM is called. It's actually an X, Y, and Z. So the image goes, and as I will show you, that actually it has a volume. So that's the difference. And so it can replace actually all other kind of imaging modalities. And it's a tremendous achievement if you think it that way. And unfortunately, I have to say it, but it is, because this, this SEM, TM, AFM together is $6-7 million instrument. And it gives you only one image at a time, one surface at a time, frozen in time. So it's a tremendous benefit having this ability of nanoscanner based. There is downside, and I'll go to that. The downside is that you do need to run that nanoscanner, which may take longer time. And then it's a two-step process. It's not, imaging is not in real time. First, we have to scan, then we have to generate the image and manipulate the image. And I'll come to the time like Miles asked. Lattice resolution scanning takes a long time. It may take more than a day, depending on how big volume we want to scan and how better resolution we want. But not always. Many of them, like AFM quality image, can be done in hours. On the other hand, there is no sample preparation. For if you know for TEM or even SCM or AFM cannot be bigger than 100, maximum 200 micron probably. But most of the AFM images are confined within 50 micron or so. Not the whole wafer, no question arises. And also, there are very specific SCM that can take a whole wafer up to 6 inch or so, but no TEM can do that. TEM is very limited. You want to see the lattice, so bigger sample doesn't arise there. Also, TEM sample preparation, which I have spent a lot of time for my PhD work, takes a lot of sample preparation, polishing the sample down to the electron transparency, and that's when we can do the imaging. But the polishing itself may cause change because it's perturbation that you are applying to a sample. Also, the high energy electron beam, both in SCM and in TEM, the high electron energy beam cause perturbation. There are, lattice is not pristine lattice anymore. And it has been found in some cases that significant variation is introduced into the sample because of those sample preparation steps. So when we are doing this without any sample preparation, looking at the pristine sample unperturbed, because terahertz is non-ionizing, it's not changing the sample in any way. All we're doing is probing and then getting the intrinsic information out of it. So there are tremendous benefit, but there are, these few things that are not done yet. I hope in the future someone will be able to do it. And yeah, Miles, you have a question.
What about a background? Is there any background or subtraction with this instrument?
You could, the software allows to do that, but if you don't use a background, then there's no background, right? But yeah, software has the option of subtracting image manipulation, all different kinds of things. One of the other thing I should mention here is then elemental analysis. In SCM, you can use the X-ray probe, and you can do the elemental analysis. Here we do spectroscopy where we can do the molecular analysis, but not elemental analysis. So that's another thing, that drawback or limitation. Okay, so any other question at this point?
One question, actually, if you can go back 2 slides where you had right here. So these are all reflected intensity, right, on the top 2 plots.
Yeah.
And you have similar scenario for transmission intensity.
I have, but I don't have that here. But yeah, we can make image in transmission as well.
Right. And can you do both
Yes.
both at the same time on the same machine, or you have different settings?
No, and at the same machine.
Same machine.
Same machine, yeah.
So
There's thing called the reflected intensity, transmitted intensity, and there's thing called transreflectance. So transreflectance meaning that simultaneous measurement of transmission and reflection and using their product or difference or summation, a lot of manipulation can be done. If you can imagine a camera system, always in reflection, right? Camera measures or makes images always in reflection. Even in a TEM, when we have the transmitted beam coming and hitting on a CCD, it's in reflection. CCD is generating the signal in reflection. So all images actually are in reflection. But we have the ability to make the image, and we have done that for some cases. It's a tremendous benefit because we can see a pattern in reflection, and then we ask the question, is it the same thing or is some artifact? When you do that in transmission, then that clarifies a lot of things, and I will show you some example of those as well.
So I'm assuming the time it takes for both reflected and transmission intensity, collecting enough data, is it similar amount of time? Like say 1 day, you said it may take a whole day for a sample for reflected case. For transmission case, is same time amount or it takes
it can be, the user will have the opportunity to decide for a given sample.
Right.
Both measurements can be done simultaneously, both reflection and transmission.
So same amount of time.
Yeah, but a lot of times they are not done simultaneously. A lot of times they are done separately for other reasons. But the machine, the instrument can do simultaneously or separately.
So sample thickness does not matter. Wafer thickness, for example, does not matter for collecting both, especially the transmission.
Most wafer semiconductors are transparent to T-ray.
Okay.
So then the reflection is important because we are probing different surface by moving the focal point in and out. So when we're doing the transmission mode imaging, that discrimination is a little blurred, little difficult.
I see.
Where the reflected mode is more important.
Okay, thank you. Maybe it's a maybe nonsense question. On the top two plots, you have the intensity kind of one is on the order of power of 6, another on the right side is power of 7.
Sure.
Is that same sample or
no,
different?
It's not same sample, it's different sample.
Okay.
Yeah. This work was done by one of our interns. He did a pretty good job actually of getting in. We have a paper where he is either a co-author or acknowledged. I forgot exactly what it is. This is one of the very early work. I think this was done in 2000.
So what is the definition of relative position? Is it compared to from a starting XY position, for example?
Oh, this stage,
or the center of the wafer.
Yeah, the stage starts at, so this 200 millimeter stage. So the current position of this stage, whatever is that's the relative position. Meaning that I could start this stage at 0 and it could go to all the way to 200,000 micron, whole length. But, sometimes the samples are conveniently placed, and then wherever it is, we measure right from that.
So this is within a given die or whole wafer relative when you're measuring?
I will come to that. I'll come to that. Okay. So
one question.
Yeah.
The next slide mentioned no elemental analysis. What about the allotropes? Are allotropes which are molecules identifiable.
I'm sorry, say that again.
The elemental allotropes, different forms of carbon, are they visible within a material as a molecule?
Good question. So allotropes are when, we will characterize some graphene samples, and you will see the allotropes they have different, although the same crystals, same chemical formula, chemical structure, but they have the lattice plane variation. So you can measure the lattice plane variation and then correlate with some kind of allotrope.
Okay.
So, for example, diamond will have quite different than graphene. And, the other thing is this polytyping or polymorphism, different type of polymorphism of the same crystal structure, that particularly in silicon carbide, this becomes a big problem. So we'll be able to see those as well.
Yeah. Okay.
Okay, so here is another little details of how the image is generated. What you call is a gridding with inverse distance to power equation, meaning that the inverse power equation need to be solved, which is done in our software. This is just for the understanding, but it's all built in the software. So we don't have to do anything. We can use the inverse gridding technique that generates the, a mesh from the measured data, and the mesh is then painted. That's how the image is generated. So general procedure of imaging is that first determine the resolution requirement. If we are doing lattice resolution imaging, then that's one way. If we are measuring so diverse kind of samples can be handled here. Let's say you want to find the defect in a 3D printed plastic material, So those defects are on the orders of millimeter probably. So you don't need very high resolution measurement there. And if we are measuring some fabric sample, for example, that would be a different kind of consideration. So first we determine or actually make an assumption what kind of resolution we need. If we are making lattice resolution, then of course there's another thing. And then we actually scan the sample. How we do it? First, we scan one line, meaning that X has a fixed number, Z and Y has number fixed, and X scan, that makes a line. Then we go to Y increment, Z is still the same, we go to Y increment, scan another line. So if we have a millimeter by millimeter by millimeter volume to scan, then G is fixed, Y is fixed, X scan 1 millimeter, then Y increment, X scan another millimeter, so on and so forth. That's how we get one surface. Once we get one surface, then we increment the Z and repeat the whole procedure again. That's where the time takes. So if we are doing just a surface image, that goes very fast. But in 1 millimeter, if we are making 1,000 surface, that will take 1,000 times longer than one surface. So, and sometimes we may have to do that, depending on the problem that we are trying to solve. The instrument allows us the opportunity to do that, unlike any other instrument. So that's the difference. And then the sample can be cylindrical as well. It doesn't have to be a rectangular sample. It can be also liquid. So basically generate image by inverse gridding, but there are other options as well. So let me show that. Oh, here are the data structures some details of it. So as I said, for every Z, every Z1, so Z1 goes to Z1, Z2 up to Zn, that is it, depth axis. Then for every Z1, you have Y1 through Yn, etc. And then for every Y, you have X1 through Xn. So I fix Z, then I go X1 through Xn, but Y1 doesn't change. For Z1, for Y1, X1 through Xn. Still Z1 for Y2, X1 through Xn again. That means same line, go Y increment and scan the X again. And all the way, it has to go from Z1 through Zn. The number Zn depends on the increment size, the depth increment size, right? Which is G start, difference of G start and G end divided by step size. Same is true for Y. Y start, difference of Y start and Y end divided by step size. And X depends on the scanning speed. So let's see if I have I don't have the front end here, but it's all spelled out in the front end. It's pretty intuitive. All the box need to be filled out, probably 5, 6 of them, and then start running it. Here, what I'm showing here is this. If we take a 3-dimensional cosine function, or sine function in this case, or any function I could take and make a 3-dimensional plot. So example of sine is shown here. It still looks like, in 3-dimensional, what it looks like. As we measure the data, we can make a scatter plot. There are things called topography and there are things called tomography. These are none of them. The imaging that we do is the real imaging, which is neither tomography nor topography. It's a image generation because the points that I measured in 3D looks like this. If I didn't do the algorithm. So until we do the algorithm, image doesn't, it doesn't make any meaningful image. So practical examples and comparisons, let me show you a few of them. Or do we have enough time today?
It's already an hour, but
yeah. So perhaps for the sake of your better paying attention, we'll start from here next time. All the examples.
yeah, one thing may be helpful for future discussion. What is the minimum increment you can do for your setup?
Yeah.
Minimum increment in the, not in the X direction, Y and Z.
Well, it's the same in all direction. We can control how the step size. So
right.
Yeah, it's in nanometers. That's the control we can do. And then the algorithm takes over to make the image.
And that minimum step size is same for
No. It's
directions?
I should put a front end. What I'll do, put a front end image over here. I don't have that ready, but I'll make it next time. Okay. So how does that work will be very clear. So in other words, user can choose the step size. We don't let the program dictate that because, like I said, when we want to make the lattice resolution imaging, we can choose the speed and step size, all of them. If there is some anisotropy in a sample, that we have a way to capture that. If the sample is isotropic, we have a way to capture that as well. So quite a bit versatile samples can be handled here. For example, in silicon carbide, there are the lattice parameter in the Z direction can vary from few angstrom to few hundred nanometer. So many polytypes are out there. I mean, in silicon carbide can happen. So all of those things can be, can be captured by using the measurement parameter, by changing the measurement parameter. There are a lot of things comes in here. So we'll go through the things that we have done. There are a lot of other things that can be done down the road.
Sure. Thank you.
Okay, so with that, maybe we can stop here today.
Yeah. Thank you again.
Thank you.
Thank you, Uncle.